Now we're going to look at multiplying a vector by a scalar. The difference between a vector and a scalar is that a vector has magnitude and direction, and a scalar just incorporates magnitude. So for example, you could say to someone, I traveled 100 kilometers. That number would represent a scalar, whereas if you said I traveled 100 kilometers east, you've now indicated a direction and magnitude, which would therefore be a vector. So let's take a look at the following example. In my diagram I have vectors A and B. If I asked you to sketch 2A, what would that be equivalent to? That would be a vector in the same direction of A, but twice as large. So you notice in my diagram vector A is 4 units up, so 2A would be A plus A, so it would be a vector 8 units up. What about negative 3b? Well, we know that negative b is the opposite of b. Since b is 3 units to the right, negative b would be 3 units to the left. And since I said negative 3b, that would be negative 9 units to the left. So there is negative 3b. So this is all scalar multiplication is taking the vector and multiplying it by the number in front of that vector. So for scalar multiplication, let v be any vector and k be any scalar. Then k times v is a vector such that kv is k times the length of v, and if k is greater than 0 or positive, then it's in the same direction as we saw above. A and 2a are in the same direction. If k is less than 0, or if it's negative, then kv is in the opposite direction as vector v, as we can see with vector b and negative 3b given in our diagram above. And if k is 0, then we have the 0 vector. This leads into our next topic, collinear vectors. Vectors that can be translated so that their initial and end points lie on the same line. Or, another way to think of it, is an angle when arranged tail to tail is 0 or 180. So here are two collinear vectors. If I arrange them tail to tail, and they're 180, they have different lengths, but they lie on the same line, and the angle between them is 180 degrees. Or I draw two vectors pointing in the same direction, tail to tail, and the angle between these two are 0 degrees. So these are all collinear vectors. State the collinear vectors in example 1. So if we go back to our example, we see that vector A is collinear to vector 2a, and vector B is collinear to vector negative 3b. So now let's try to answer the following question. Is scalar multiplication distributive over vector addition? So if you think back to your distributive property, if I have k times vector A plus vector B, could I take that k, bring it into the brackets, and say that is the same thing as taking k times vector A plus k times vector B? We're going to prove this geometrically at the moment, and then verify this later when we talk about algebraic vectors. So let's look at the proof. So we're going to start off by looking at vectors 2a plus b. So this is saying find a plus b and multiply it by 2. So let's do a plus b. So a is 1 left, 3 up. So let's draw that. 1 left, 3 up. There it is there. And vector b is 3 to the right. So there is vector b. So a plus b is of this vector here. And notice that's 4 to the right and 3 up. So this is a plus b. So the last thing is to double a plus b. So if I'm going 4 to the right and 3 up, let's do that again. 4 to the right and 3 up. So this vector right here, going from here to here, is 2a plus b's. So is that the same thing as 2a plus 2b? So this is the first part we've proven. This is 2a plus b. So now let's take a look at 2a plus 2b. That'll be this portion here that I'm going to draw. So first let's draw vector 2a. So 2a would be 2 to the right and 6 up. So 2 to the right and 1, 2, 3. So starting here, 2 to the right and 6 up. So there is vector 2a. Then we need 2b, which is 6 units to the right. There is 2b. And let's draw 2a plus 2b. So that would be this vector here. That's 2a plus 2b. And now if you look at these two vectors here, so this one right here and this one right here, hopefully they are equal vectors. So let's count. So 1, 2, 3, 4, 5, 6, 7, 8 to the right. 1, 2, 3, 4, 5, 6 up. So this goes 8 to the right, 6 up. Let's check. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So now we've shown that these two vectors are the same, that 2a plus b is equal to 2a plus 2b. So we've only shown 2, but we could do the same thing with 3, 4, 5, any number we choose, and we would prove that scalar multiplication is distributive over vector addition. Last example. Let's assume that AC is the same thing as vector A, so this is vector A, and AE is the same thing as vector B. I want you to write AK, so here's A to K, is this vector right here. How can we write it in terms of A's and B's only? I could travel vector A, and then I could travel 2 vector B's, and I can get to the point K. And this is what we're looking for. So AK is equal to vector A plus 2 vector B's. So let's try the next one, FD. So F to D is right here. So the path that we could choose is going this time negative B, and then following vector A. Or if you like, we can follow path of A, vector A, and take negative B, right? This is A, 2 units to the right, and this is negative B. Or go 1 unit up, which is negative B. So this one we can say is equivalent to A minus B. All right, let's try the next one. So L to G. So here is L to G. So let's talk about A first. So this would be the path. So this would be A here, but this would be half of A. So I can take half of A and going in the opposite direction. So this would be negative half of A. And then going up again, this would be negative of B. So for this result here, we have negative 1/2 of A. And then if we take minus B and add those two up, we would get vector LG. And finally, let's take a look at vector L to I. L to I is just this vector right here. So we don't need vector B in this one, but we need the negative of vector A. Remember, this is vector A right here. And how much of vector A do we need? Well, we need 1/2 of vector A, or 3/2 of vector A's in the opposite direction. So this would be negative 3/2 of vector A. So this example leads into this definition. Linear combinations of vectors. We combined 2 vectors to make 1. So if A and B are non-zero, non-collinear vectors, remember collinear means they are 180 degrees apart or 0 degrees apart, then any vector V in the plane containing A and B can be expressed as a linear combination of A and B. That's all it's saying. It's saying I'm going to take this A and this B, I'm going to combine them together to get this result here. How can I combine them to make it work? You're saying, well, how? Well, we just did it up here. Look at these examples. We took negative 1/2 A minus B and made vector LG. We took FD and that was A minus B. So we can combine vectors, and the fancy term for it is the linear combination of vectors. So again, try the following questions and let me know if you need any help.